derived quantities. Now, this is one of the building blocks as far as physics is concerned, and this is a very important topic that is going to help you in understanding future concepts as far as physics is concerned. So, in today's class, we are going to be learning on these 4 bullet points. These are going to be our objective for today's class. Number one, we should be able to define fundamental quantities and units. Two, we should be able to outline examples of fundamental quantities. Three, we should be able to define derived quantities and units and outline their examples. And finally, we should be able to define dimension of physical quantities and outline practical example. So let's dive into the lesson in proper. Now, fundamental quantities, they're also known as basic quantities, and these are quantities that are independent of other quantities, and they can be defined in terms of other quantity. They cannot be defined in terms of other quantity. Now, let me use the creation. We say God created the heavens and the earth, then as time goes on, he decided to create other things. Now, God Himself is fundamental because He has been in existence before every other things were in existence. So I want you to treat these fundamental quantities as quantities that are already existing and they are independent of other quantities around. So they have been in existence before other quantities. So let's look at examples of these fundamental quantities. According to physics, we have three major fundamental units. Of course, we have more than that, but these three are what governs the existence of things on Earth and also in the universe. So I'm going to explain why I said that. Now, we have length. As far as this universe is concerned, there's need for measurement. There's need for measurement. Now, we know that in Earth, we have different countries, right? We have boundaries, we have measurements, we have where countries have their boundaries and all that. So these boundaries measured by length. So that's why we define length as an extent of space or distance extended. Secondly, we have another fundamental unit which is very important, which is mass. Now we know mass is the quantity of matter or material in a body. Even the earth has mass. Whatever object you see around you has mass. So that is why it's a fundamental quantity. Then finally, we have time. There is no event that happen in space or on earth that is not measured with time. That's what makes time a fundamental quantity. So here we define time as distinguishable events with reference to before and after. So if you want to embark on a journey, we have the before, we have the after. So time governs every activity as far as Earth is concerned. So let me make a recap for fundamental quantity. So have it in mind that fundamental quantities, these are basic quantities that are independent. Independent is the key word. These are basic quantities that are independent of other quantities. So we move to the next. Here we have the examples of fundamental quantities. So we have length, and the unit for length is meter, and the abbreviation is capital M. Then we have time. Time is second, and the unit for abbreviation is S. We have mass, and mass is measured in kilograms. So here we have kg. Actually, mass is measured in kilograms and grams, but we use kg as the major unit. Then we have electric current, which is measured in ampere. That's the unit, and the abbreviation is A, capital A. Then we have temperature. Temperature actually is measured in three different units, but Kelvin is the approved unit. We have degree Celsius, we have degree Fahrenheit, but Kelvin is the most suitable unit because I think we have derived quantities. So this unit is part of what is being used. Then we have amount of substance. Amount of substance is majorly in chemistry. When we talk about elements and compound, we talk about the amount in mole of those molecules. So we measure those amount of substance in those compound using mole, and the unit for mole is mole, mol, without the e. Then luminous intensity is simply talking about intensity of light. So this is measured in candela. So that's the unit for luminous intensity. So these are the fundamental quantities as far as physics is concerned. So let's move to derived quantities. Now, we have defined fundamental quantities as those quantities that are independent of other quantities. However, derived quantities are those units that are obtained by simple combination of our fundamental quantities and units. So here we're going to be taking a practical example. Here on my screen, we have derived quantities, and we're going to be seeing how these derived quantities are gotten from fundamental quantities. So our first example here is area. The formula for area is length times breadth. However, length is a fundamental quantity. Breadth is also a fundamental quantity. Breadth is simply length, but in a different dimension. So both of them are fundamental quantities. So combination of these two fundamental quantities give birth to our derived quantity. And since length is measured in meter, meter times meter will give us meter square. That's why we get our m square, which is the derived unit. Then next is volume. Now, for you to measure a volume of a shape, you have to multiply the length of that shape, the breadth of the shape, and also the height. Have it in mind that length is a fundamental quantity, breadth also is a fundamental quantity, and height is also a fundamental quantity. All of them are categorized under length, but it depends on the dimensioning and the placement of that particular distance. If we are going below the ocean depth, we measure that, we call it depth. You can say the depth of the sea, but it's still length, right? So if we want to measure the height of a building, we call it height, right? That's because the length is going upward. So all these are fundamental quantities, just depending on their positioning. Now, for the derived unit, since we are multiplying length in three places, we are going to have m times m times m. That is giving us MQ. That's how we got the unit MQ for volume. Now we move to the next. Next is density. For you to know the meaning of density, density is simply mass per volume. What is the mass of this object per the volume? So how do we get to the derived unit? It's simple. We ask ourselves, what is the unit of mass? From the previous slide, we say mass is measured in kg. So we have kg per volume. What is the derived unit for volume? We have mq. But since we have division in between the formula, we say kg meter per. You can see the minus 3. That minus stands for division. If it was mass times volume, we have kg meter cube. But since we have mass over volume, it's going to be kg meter minus 3. So that's why we have negation in that particular number. Moving on, we have velocity. Velocity is simply the displacement of an object with respect to time or per unit time. So velocity here is displacement over time. Now, what's the unit for displacement? Displacement unit is measured in meter. It's measured in meter because it's still sharing the same property with length, just like I said earlier. So displacement is measured in meter, time is measured in seconds. So since we are saying displacement divide by time, that's why our formula here is meter second minus 1. We call it per time, displacement per time. So our derived unit is going to be meter per second. That's why we have that minus 1. So next, we move to acceleration. Acceleration is simply change in velocity over time. Now, velocity, what's the formula for velocity? Velocity, just from the previous example, it says displacement over time, and the unit for the velocity is meter per second. So we have meter per second again because we say change in velocity over time. So change in velocity is meter per second, just from the previous slide here. Since we're going to divide it by time again, so we're going to be having meter per second per second. So we're having 2 seconds now. So that's why our derived unit is meter per second. We have